Welcome to Similarity Modeling 1 and 2, the lecture blocks on seeing and hearing in computers. My name is Horst Eidenberger. The educational goal for this module, which is named Spectral Modeling, Spectral Models, Spectral Features, are threefold, as most of the time in this lecture series. The first goal is that you understand the role of integral transforms in spectral modeling and in similarity modeling in general, so in the area of feature engineering. Integral transformations include most famously the Fourier transformation, which is based on the Laplace transformation. You might remember the Laplacian operator from the feature engineering lecture that will re-emerge in various places in this lecture again. Fourier transformation is of exceptional importance in the audio domain. And there are also others like the Cosine Transformation that is used in compression mostly, image compression and video compression, but also plays a role in media understanding. I will show you visual features that use it and also, surprisingly, audio features for a particular purpose. And we will briefly touch wavelets, which is a generalization of the idea of integral transformation, and a few parametric transform, most notably the half transformation. Okay, based on these transforms, we will develop a toolbox of spectral features, mostly in the area of audio, where they are of the highest practical significance, despite the revolution of deep learning, but also in the area of visual encoding in different roles, just to a lesser degree. I presume that most of these features should be very important or usable in the context of your lab course. There will be a separate block, a very brief block on hints, what you can do in the lab course in order to optimize the performance of your project, but that comes later, not in this block. Okay, eventually, because it fits very nicely with integral transforms and feature description, we will provide a very small toolbox of so-called local feature extraction methods. The motivation for that is that they are as integral and as holistic as the integral transformation, so they're always employed on the entire image and they serve the same purpose. They're trying to eliminate or reduce the influence of the gravity of the sample, one of the fundamental problems that are named in the first lecture on the setting Similarity Modeling 1. So all of these methods are targeted towards overcoming this gravity of the sample. Please be aware this is a term that only I use. It's not a common term in the field, but it describes it very well. If you have problems, questions, anything, and cannot clarify them by watching the videos, please post a question in the forum of the e-learning course that goes along with these lecture series. The link can be found at the end of the video and as well in the TU Information Systems. Get in touch with your lecturer, with your colleagues, and discuss topics that are still muddy after watching the videos. So first integral transforms, spectral features based on them, and local features as an add-on to the spectral ones. Hope you enjoyed. Okay, let's start off with a slide that I have shown a couple of times already. It is one from my book, Handbook of Multimedia Information Retrieval, which as a course book can be found for free download on the site of the TU e-learning platform. In the whole form with the text, but also only as a set of figures in a separate PDF file, both linked on the same page. Okay, today we deal with the same aspect of visual and audible media that we have dealt before. We are in the visual area of images and video concerned with finding edges. That is a steep change in luminance, in brightness, between two localities of a visual object. Localities might be one frame after the other if it's about motion, or might be one neighborhood of pixels spatially next to each other if it is about image data. In contrast, music, speech, so the audio signals, are of a completely different nature. The information lies in the distribution of the samples, not in the individual samples. Therefore, we need to cover or describe them in the modeling process in a holistic way. We have to find the fundamental frequencies, different here for music than for speech. And once we have found the fundamental frequencies, we have to identify the overtone structures. Whereas in the visual field, it is really about edges, corners, and the elimination of noise. Noise is essentially everything in between, all the big blobs that we are not interested in. So two fundamentally different problems. One of them can be solved with time-based features, as we have seen in the lecture on feature engineering. That is the image domain. For the for the audio domain, it is not sufficient to work with time-based features. Yes, we can find out the fundamental frequency by counting the zero crossings and get a fair approximation of what it could be. However, when it comes to identifying overtone structures, frequencies that build on the fundamental frequency and drive, for example, the timbre of a trumpet versus a trombone, we are completely lost. The same goes for identifying formants. The state-of-the-art tools in voice recognition, such as Pratt, for example, or most importantly, it's a free software, all employ Fourier transformations or a particular form of integral transformation to do that. Because from the time information from the individual samples, it is not directly extractable what the smaller frequencies on top of the fundamental frequency, the overtones, actually are. So let's have a look how it is done. And let's go back to 2.5 centuries almost. In the year 1785, that is how the story is usually told, a French mathematician by the name of Laplace, a count, I think, saw himself in the same situation that many other mathematicians saw themselves before the invention and development of computing machines. He wanted to do mathematics, he wanted to find out about certain problems, for example, solving particular types of differential equations, and that included a heavy amount of computing. But for this computing, all he had available were human computers. Well, human computers suffer from 3 essential drawbacks. The first is they make mistakes. The second is they are costly. And the third one is that they actually don't scale very well. So they are slow and cannot do multiple tasks at the same time. Well, despite the works of Mr. Babbage and Miss Lovelace, computing machines were still far away, also for mechanical reasons. So he thought about a way to reduce the amount of computing he would have to take. One thing he thought of was to get a transformation that brings him from a space where he has to do multiplications to another space where these multiplications can be replaced by additions and subtractions. The idea would be to take a problem, transform it into the other domain, solve it there with simpler arithmetic operations, and then transform back. So for Laplace, important was to have an integral transformation plus a back transform. That was very important for him. he wanted to go somewhere where computation is simpler and be able to get back and have the guarantee that all the computations are still correct. So what he came up with was a form of positive convolution. He would take the input signal, let's denote it as f, and fold it over some kernel k, and that would bring him into the so-called spectrum. So the input function is one that goes over time. It's convoluted by positive convolution. And it employs a kernel function. That in 1785 was a very interesting formulation and a quite novel idea. And he was able to provide the proof that he could employ the same kernel to get back from the spectrum and the same operation, convolution, to the original time domain. And that was what he had wanted, a back transformation. And this he could do for one particular kernel, k being of the time domain and the spectral domain, e by the power of minus x and y. So it was an exponential function. Laplace would prove that with that kernel, those two expressions would both be true. He could build a spectrum, and from that spectrum, he could go back in the time domain. The particulars of that transformation were that it would allow him to do in the spectrum simpler computations with requiring less time, therefore less resources, and less prone to errors, which would solve the problem for him. That was fair enough, but it's still far off what we do. The next important step came, I believe, in 1823, when the Baron Fourier suggested to do a different k and use a function e minus I, the imaginary number, square root of minus 1, x and y, instead of the Laplace kernel. And that was the birth of the Fourier transform. Fourier would prove that he could build a spectrum with that in this spectrum certain computation would become easier, that he could shift here and there. There's quite a few intriguing properties about the Fourier transformation that are very relevant in certain areas of signal processing, but not here for us today. Therefore, we will skip that. And he would also have the back transformation. With this Fourier transformation, it might appear to you quite awkward that he just added the imaginary number and considered it an improvement, because apparently this formula, this kernel, is more complex than Laplace's original kernel. That is true. However, we know from the so-called Gaussian equation, which can easily be derived by yourself, that this exponential term is equivalent to the cosine of x and y minus imaginary number and the sine of x and y. And that gives us an interesting perspective. And that perspective is this hard to interpret term that is, by the way, highly similar to our generalization function that we had in the similarity modeling block. But that is just a side note. That was hard to interpret is now being interpreted in the form of angular functions. And with angular functions, we know exactly what they look like. Both sine and cosine have a structural form like this. So interpretation would be much easier of the spectral values, of the spectral coefficients as they are called, the interpretation of the coefficients would be much easier for the Fourier transformation than it was for the Laplace transformation. That was one big advantage. And that is the one that is relevant for us. Because with the sine wave, and the cosine is just a shifted sine wave, with the phase shift, we have, for that we have applications actually. And our applications are to use the spectrum in order to approximate audio features. Why that? Because a sine wave is, in the context of audio, is a pure tone. For example, of C0, 440 Hertz. Or is it C4? Okay. Sorry. A pure tone is not pleasant. No? It doesn't have any overtone structure, so it is nothing that you would actually want to have. However, it gives you a nice way of interpretation. So, for a second time, Laplace had a certain need and developed the integral transform. Fourier suggested an improvement for the sake of better interpretability and other advantages. But for us, it's that. Now we say we have an application for that in the audio domain because a sine wave is the same that we also have for a pure tone. Why do we have this link? Because of the way the kernel is combined with the time signal. It is done by positive convolution, and that is, as we know, a similarity measurement operation. Therefore, Fourier transformation compares the input values in terms of audio, the amplitudes of the membrane of a microphone or a loudspeaker respectively, compares them to a set of different sine waves with different frequencies and different offsets for cosine and sine. So the spectrum is actually a set of coefficients that measure similarity to a sine wave of 110 Hertz, 220, 440, 880, and all those in between. So for different coefficients x, the coefficient, or for different parameters x, the coefficient y tells us how similar is the input signal to a sine wave of exactly that frequency. And that is the fundamental property why the Fourier transformation is so big in the audio domain. Please try not to forget that. We have a similarity operation, we have a well-defined kernel which we can interpret in the context of our domain, which is audio, and therefore we know exactly what the output coefficients of the Fourier transformation are. They say the tone with 440 Hertz is that important or not? Almost, unfortunately. Why almost? Because there is one little problem with the Fourier transformation, and that is the output is not just a real number. The output is, unfortunately, let's make this in red because it's so important. It has an imaginary part. It is a complex number. So, how do we deal with that? The usual way to deal with that is twofold. One is, in the audio domain, to throw away the sine wave and just use the so-called real FT. I will show you examples for that in a minute. That is one way. The more common way is to take the so-called magnitude of the spectrum by computing the Pythagorean for the real part plus the imaginary part. Square them both out, sum them up, and compute the value. If you divide them by 2, which is normally not done, but you could do it, then it would be a root mean square of the whole spectrum. And that is then called the magnitude. So, if you do that, you have dealt with the problem of complexity in the spectrum. The interpretation is like that with sine waves. Now, if you think about that, what you're actually comparing the Fourier, your input signal to, is not a sine wave, but it is something that looks almost like this. That is the result of the magnitude computation. So it's not, even though signal processing people to this day pretend it would be comparing the spectrum of the Fourier transformation would be sine waves, it is rather something that looks like this, which is a close approximation to what the sine function actually looks like. However, it is not purely the same. So if you compute the Fourier spectrum and want to employ audio transformations on it, it is always a good idea to do some post-processing. There are different procedures, but that would lead us too far today. So, once again, we had kernels, we had input signals, the time domain as it is called. We transform by measuring similarity to a plethora of different almost sine waves. The outcome can be interpreted, in particular for the audio, as giving the importance of certain frequencies in the input signal, thus maybe allowing us to identify a particular singer or a particular instrument and whatsoever. Now the last thing in this particular context is that in our domain, similarity modeling, we summarize, we never transform back. So we don't care about the back transformation, which was important for Laplace and of course important for Fourier and all the others who were involved in the development. It is not important for us. Therefore, we can actually take just the real part of the Fourier transformation and use it in feature modeling, because we never have to go back to the original domain. There is no reconstruction of the signal. Please keep that in mind. Okay, having said that, let's look at a few properties, and for that I printed a couple of functions from the book. The first one is a simple description what transformation actually means. Transformation might mean that I have a uniform block in the visual area, that I have a horizontal transition from bright to dark expressed by that curve, no? That I have something changing back and forth with high frequency information like this. There's another uniform block and one more uniform block. That only very quickly. So it's all encoded in the one-dimensional signal, even though in the terms of video we are actually speaking of an at least three-dimensional data type, if not more, if it's a stereo video, for example. So, what happens if you apply the Fourier transformation on an input signal? I would like to show you this on the example of the square function with this frequency, just looking like that. If you employ a Fourier transformation and use all 100% of the coefficients in the spectrum that you have, then you get the original signal back. Why? Because it's a guaranteed back transformation for the full Fourier transformation. If you take all the complex numbers that form the spectrum and go back to the original signal, it looks like this. However, if you want to summarize in the event, you have to throw away coefficients. Otherwise, it's not a summary. It's still the original amount of data. If the original had 1 megabyte and you keep all the coefficients, you still have 1 megabyte of data. That's not the purpose of similarity modeling, though you throw away coefficients. Let's say we have thrown away the not the entire imaginary part, but we have thrown away 2/3, so 68% in this case, of both the real and the imaginary coefficients, and reconstruct the signal from that. Then it looks like this function. And what do you see here? What you see here is twofold. First of all, the horizontal lines, so many samples that have a uniform value, are only approximated by a curve that has a certain frequency. Why? We threw away not just random coefficients, but the coefficients with the highest frequencies, with the highest overtones. And that is then what is missing in the signal for smoothing the horizontal part of the signal. Okay. Furthermore, what we see is that the vertical transgression from one area to the other is now actually a bit not as steep anymore, and it takes multiple samples to get from the one level to the other level. That is what happens. If we are even harder and throw away everything except 8%, so 92% of the highest level frequencies, then we see the effect more clearly. First, everything that would require high frequency information is now only represented by a few samples. And everything that would require the precise definition of 2 neighboring samples is now distributed over a whole set of different coefficients, like 5 or 10 or how many. And the effect gets worse if we throw away another half of that spectrum and now end up with just 4%, then we have essentially left the sine wave of the fundamental frequency, plus a little bit of what rather appears as noise than a helpful component of the signal. It is helpful, though, if we have the other parts of the signal, it would constitute eventually the step function that we had up there. So the Fourier spectrum apparently orders frequencies from the most fundamental in the first coefficients to the highest at the top level. Why is that? Because the sine waves employed in the kernel have increasing parameters. It's the product of the time domain and of the spectral domain. That means that number gets higher the further up we go in the spectrum, and therefore we end up with higher level frequencies. The first coefficients are low, it's the sine of a lower function, and if the parameters rise more quickly, then of course we have a higher frequency and a shorter wavelength of the individual sine wave. Okay, so this is a fundamental property of the Fourier transformation. Okay, let's look at a few other properties. If we do what we do, this is, you might remember, the image signal from the MSNBC broadcast going through the nose tip of the anchor man. We had it in the setting and we had it in a couple of other lectures. And below you see the Fourier spectrum of this signal over its entire length without any smoothing at the edges. We come to that in a minute when we speak about that. In this case, I just brutally computed the Fourier spectrum without caring about the borders and border effects that appear in the Fourier transformation, such as pre-echoes and others, which you might have heard of in multimedia lectures. Okay, so what does the Fourier spectrum look like? For an image signal, apparently The vast majority of the information is here, so there is something like a fundamental frequency. It is not clearly defined, but it peters out into the area of the base signals. And there is a lot of high frequency information. These minimum deviations are smoothed by the high frequency components. There is hardly anything in the mid-range. Why is that? Because we said in the visual domain, the information lies in the edges. And the edges are low frequency information. The noise of the small changes appears to be information, has an informative quality, but is semantically not relevant, is encoded in the upper part. So would we employ the Fourier transformation on visual material, all spectrums or most spectrums would look the same. The whole information would be compressed into just a few coefficients, the earliest coefficients that we have in the material. And there would be top-level information for the fine gradations. So it would actually be split into two components, one here and one here, because the nature of the signal and of the underlying sense, the visual sense, our saccadic seeing and scanning of object shapes based on their luminance is structured like that. Okay, so I said that I didn't care anything about the borders. If I don't do that, which in practice you never should, I'd get into a lot of troubles, because the Fourier transformation is sensitive to what the first signal actually looks like. Applied on the same signal that we had before, we see that we apparently have enormous artifacts if we employ the Fourier transformation. And these artifacts are already after we employed a certain trick. What we did is we took the input signal, so F, and folded it. Well, now it's not a convolution operation, sorry, but did an element-wise computation with a so-called window function. Window functions appear in many forms. Here are three famous examples. That is the Hamming window, which looks like Gaussian. There is one with a very similar name and similar shape, yet completely different, which is the Henning window. This simple triangular shape is the Bartlett window, and the Kaiser window looks like a sine function, and there is also a simple square function if you don't do anything, just as I did in my example. If you do that, do the windowing, and only then employ the kernel in order to compute the spectrum, you end up with spectra that look like this. Apparently, the Bartlett, in comparison to the original signal, already reduced the artifact at the beginning and a little bit at the end. Hamming window, similar. Kaiser function was successful at the end, but not at the beginning. Apparently, we're still facing a lot of problems. It is a matter of taste which function you employ. You should leave it to quantitative experiments which you use. However, you should use in your experiments always, if you go for the Fourier transformation, you should always combine it with a windowing function, and the Hamming function is one that is very frequently used. Let's put it that way. By the way, what does it do? It means that coefficients in the middle are fully added to the input signal, whereas those in the beginning and at the end are compressed to almost zero. If that is the case, the Fourier transformation cannot do much wrong, because the first few signals only slowly fade in. And it's the same fade out at the end. And with that, we hope not too much can actually break. That is a processing step that is known as windowing. Very important pre-processing. We will see it when we talk about the features. Okay, the next thing that we want to have a look is more characteristics of the Fourier transformation versus other transformations. So far we know only Laplace and Fourier. One more transformation is known as the discrete cosine transform. It is defined in a number of different forms. We use the DCT2, I believe is the name, which is defined that the spectrum, or the kernel actually, looks something like cosine of p by the number of samples multiplied by x plus a half multiplied by y. So what we have here is a function that is dependent again on x and y, but in a little bit, and of course on some constant, half and p divided by the number of samples, not so important. So in essence, the kernel is the cosine of xy plus y half. Not fully correct, but sufficient. Okay, the rest of the operation is exactly the same. Spectrum is computed by folding the kernel over the input signal. There is a back transformation, therefore the cosine transformation is, for example, heavily used in image compression and in video compression. All MPEG formats employ this function, and so do the JPEG formats. Not even JPEG 2000 was able to push the cosine transformation aside. And why is that? Let's have a look at this image. It's another one from the book. It shows us our Anchorman again. And it shows us the same idea that we had on one of the earlier slides. And that was, we do the spectral transform. And we remove coefficients. And then we do the back transformation and have a look at the outcome. This for three functions: Fourier transformation, cosine transformation, and a so-called wavelet. What that is, I will explain to you in a minute. If we do that and we leave 99% of the coefficients and throw away only 1%, then you can see that in the Fourier transformation we already have a dramatic loss of information. By just removing those high frequency components, we already lost half of the shape. There's hardly any relevant information left anymore. If we go down the ladder, it further deteriorates spectacularly. At 90%, just 10% have been thrown away. Please remember, we are almost unable to recognize the image, and it goes further at 5%. It is almost completely gone. In comparison, the cosine transformation at 99% looks indistinguishable from the original image. It's the same for 90%, and it's still almost the same for 50%. There is a small fade in the saturation of the image, but that's it. Even if we throw away 90%, we are still able to recognize the face of the anchor person. Only if we remove 95% of the coefficients, the codec, as we say, breaks down, and the back transformation is not able anymore to reconstruct the original image. It is similar for the hard transformation, but actually the hard transformation already breaks down one level earlier. At 10%, phase features are gone, whereas in the cosine transformation, at 10%, they are still there. What can we conclude? Two things. FT apparently distributes the information in the original signal onto the entire spectrum, or as we already know, into the very low coefficients and the very high coefficients when it comes to image material. For audio material, which is uniformly distributed, it will put it in all coefficients. So it maintains the distribution of high and low level information. In comparison, the cosine transformation is a strong discriminator. It somehow manages, we don't know yet how, but it somehow manages to get the most important coefficients apparently into the first n. Even at 10% coefficient, the image information still survives. So it managed to get all the relevant information in the original stimulus into the first 10%, because the other 90% have been thrown away. But still, if we do the back transformation, the anchorman is back. So it is kind of a discriminator. That is a highly interesting property of the cosine transformation. Fourier distributors uniformly, cosine even more extreme than a wavelet transformation, which comes in a minute as a brief description, is able to get all information pushed into a small subset of the features. Now the question is, how is that done? For that, since we employ the same function for both Fourier transformation and cosine transformation, and the role of the positive convolution is always the same, the input signal cannot be influenced by us, the magic must necessarily lie in the kernel function. So let's have a look at the kernel functions. In the Fourier case, it is this function. In the cosine transformation case, it is this function. Here in this Fourier transformation, we employed the magnitude. In order to compute the spectrum and go back from there. So this is our function. So apparently, if we use sine and cosine in the same function, then we get, because of the phase shift, the uniform distribution. If we go just for the cosine values and furthermore add a second running variable, the y again for the spectrum, to increase more rapidly the frequencies in the kernel function, then apparently very soon we pack all available information in the coefficients, and later on only have small gradations. This is a very important finding. The cosine transformation is a discriminator. Matter of fact, it's such a powerful discriminator that it is even used in the audio domain and in other signal domains. I emphasize this point because students tend to, and also scholars actually in papers, tend to confuse these two things. Yes, the cosine transformation is an integral transformation. Yes, it can be used to do a back transformation. That is all true. But that is not where its strength lies. Its strength lies actually in doing a factor analysis, a principal component analysis, in getting the signal information into a few coefficients and conveniently storing them as the first coefficients of the spectrum. That is very, very nice. So it is actually factor analysis. It is a compression method, a discrimination method, despite being an integral transform. Okay? The classic integral transform, Fourier transformation, behaves differently. Please try to keep that in mind. We will see a couple of examples in a few minutes. Before that, I would like to point out what this half wavelet thing was that I just showed you. The half wavelet is a little function that looks like this. This is called a mother wavelet or phi. This one is simply defined as in a certain range give us the value of 1 and in another range give us the value of -1. Other wavelets are defined in a more complex way, like this Debussy wavelet. and the wavelets and so on. We will come to a few more smoother ones on the next slide. But how do we apply such a wavelet function? It has two properties. The first one is it is limited. Since it's limited in comparison to a cosine function that is defined for every value on the x-axis, it comes up with a different property. It can be used local. That means I can employ it not just on the entire signal by a proper process, but I can employ it at the particular position. And what you do with wavelets is that usually you define a so-called phase by transforming the mother wavelet by two parameters, something like that. I really have forgotten. One is the size parameter S, and the other one is the location parameter, which is just the bias, the offset. And build a base. That base might consist of 100 variants of the wavelet, one being shorter, the other one being longer, and so on. So many possibilities do exist. That is controlled through the size parameter, and the location in the signal is defined by the L parameter. Now you will say, well, if I make only a small base, then I have holes in the distribution. That is correct. And that is remedied by going in a loop. That means taking the original signal, employing, again, by positive convolution, this kernel function onto the original signal. Gives you a first spectrum, but it also gives you the rest of the signal which has not been transformed, all the other locations. Those are then usually divided in size by 2, so you shrink the input signal. If before it looked like that, then after shrinking it will look like that. And then employing it again and again, and that builds you a pyramid of coefficients. If you do that until the original signal by contraction vanishes to 0 or to a small residual, then you actually have transformed the entire signal. That is the idea of the wavelet transformation, very popular in the late 90s when I was a young PhD student, when JPEG 2000, for example, was defined. Nowadays, not so popular anymore because Cosine transformation is so hugely efficient and in particularly strong in the video compression domain. And of course, the development of fiber networks globally has taken the pressure out of video compression anyway. But still a powerful method. However, we have seen this Haar wavelet, which is considerably older than the whole wavelet theory. This is from the early 20th century, is not as powerful as the cosine transformation. We have seen that Haar wavelet breaks down before the cosine transformation breaks down in the information content. Still, I thought you should hear that and be able to employ it. Okay, like these one-dimensional wavelets that are all discrete, so we have a steep transition from one thing to the other, very good in the image domain, of course. We have also more continuous ones. A simple form is a simple Gaussian, looks like that. If you do the second derivative of the Gaussian, you end up with the so-called Mexican hat. And also very important is the Gaba wavelet, which also is very old from the time between the wars. It has a number of parameters for the amplitude, for the size, for the location, for the frequency. It was also an early case of how you could encode image information. So keep in mind what the Mexican hat looks like, and the Gaba wavelet of the Professor Gabor is also an important feature that is used again in the same form of convolution and with a pyramidal algorithm on some input signal in order to provide some spectrum. Okay. Lastly, in that area, I would like to show you two transformations from the optical industry. These are the so-called Sanika Moments. All these pictures come from the slide set that is on the e-learning platform. These were originally defined to find cracks and faults in the quality assurance process of the optical industry. So a mathematical formulation defines visual properties or visualizable properties that are similar to certain types of artifacts. If I convolute these moments, these functions, over some input signal, which would be, of course, the image of a lens that was photographed in sampling, in quality management, in the optical company, then I arrive at a spectrum. If the similar is for something that is not desired beyond a certain threshold, then I set an alarm and say there is an error in this sample. Have a closer look. Okay. Last one from this area is the angular radial transform, which was quite popular in the 1990s and is used in MPEG-7 for visual features. It's yet another kernel, very similar to the Zernikas if you look like them, but more quickly going into higher frequencies. Application is the same, idea is the same, yet another kernel, so a bit other interpretation because, as you know, at the center is always similarity measurement through positive convolution. Okay, that's it for the integral transform. But before we go to the features, very briefly I want to show you two so-called parametric transforms. What's the difference? Integral transforms, we said, guarantee a way back. So you have a spectrum, you have a way to compute it, and there is a way back from the spectrum to the original domain without losing information. That is very important in many signal processing areas. It is not important in our area. Media understanding doesn't need a way back. We still have the original media object for reference, and the summarization process, we don't need to go back. There is no verification step on that level. Parametric transform provide exactly that. They give you a way to project from one area to another, from time to a spectrum. They give you some desired properties, whatever they are. These desired properties can be managed through parameters. That's why they're called parametric transforms. And once you are in the spectrum, there's no way back. One of them is the Radial transformation, which is very simple. You define a rotating axis, this here, and let it rotate 360 degrees over the center of an image most of the time, but it could be different location as well, of course. Doesn't change anything. And then you summarize the luminance values for that particular position. And you do that for all the angles. And that gives you something from which it is very hard to return to the original domain. It's not fully impossible, but it's very hard to do. But something that also contains all or the vast majority of the visual image information. And you can use this as a pre-processing for feature extraction, thus providing you something that is desired property, rotation invariant. If you have to do that in a deep network, actually you would have to learn all rotations depending on the type of network that you have, which is costly. To say the truth, Radial transformation is also very costly. It is extremely slow. However, it is a classic of feature engineering and I wanted to mention it. To show you a few examples before we go on to the next and then last parametric transform, no matter what the input stimulus has as orientation, the output spectrum is either the same or 180% rotated and can easily be identified by its peak and rotated back. So independent of the individual rotation, if I apply the Radial transform first, I get this desired property of whatever the outcome is, it is rotation invariant. A second thing that you could employ is the Huff transformation. The Huff transformation for every point in the image computes the length and orientation of the gradient and stores them in a histogram. So for the different orientations, you store the number of pixels that have this orientation. That is very handy if you have a typical pattern, like a texture, checkerboard for example, something like that. Or if you're looking for long lines that seldom occur, maybe in an image of an image situation where you take a webcam in order to film something that is of rectangular shape, then it is easy to find, usually by using the Huff transformation, the outstanding edges, the longest edges that you have, by simply counting these values of orientation and gradient. It gives you also rotation invariance, but the desired property here is mostly to discriminate long edges. So you don't have to do a complex form of image analysis. You just do edge computation, like with the Sobel operator, for example, employ the Huff transform, and there you have discriminated those who are predominant in the image. So much for parametric transform. That finishes the part on the integral transforms. Now I would like to go on and show you where you can employ transformations, integral transformations. So let's make two blocks for the Fourier transformation and for the cosine transformation. And let's start off with the Fourier transformation. That is, for example, used in the audio domain for so-called spectral peaks. How do you do that? You employ a so-called short-time Fourier transformation, that is a windowing function, framing of like 40 milliseconds, 80 milliseconds, 1 second, as we had in feature engineering, and then the Fourier transformation employed in the discrete form, of course. Practically, you will do framing first, windowing second, and then the Fourier transformation. So this is just a list, not the process. That is the short time Fourier transformation. Once you have done that, you do the magnitude of the spectrum, because you can't count imaginary numbers, and then you find the max n, like 5, in this magnitude spectrum. And that is the recipe for spectral peaks, a feature that, as far as I know, is used in certain audio apps for the recognition of particular tunes. So what you do is, in bits of 80 or 40 milliseconds, you look for the most important frequencies, and then the next important, next important, next important, by this recipe. Another audio domain feature that you have is you can employ it in rhythm detection. here the typical recipe is to do the short-time Fourier transformation. Secondly, employ the Barkhausen critical bands transformation, or let's say transformation. With the Barkhausen, you get 25 critical bands, and for each critical band, you employ then linear predictive coding. Barkhausen we had when we spoke about perception, and linear predictive coding we spoke about when we spoke about feature engineering, and the whole process is referred to as psychological or psychophysical linear prediction. Okay, so these are two heavily used features. As I said when we spoke about feature engineering in the time domain, you don't have to implement these features by yourself, but there are libraries in Python referenced in the e-learning course, but also for all other major systems that already provide you these extraction methods. Okay. A third thing that you want to deal with is timbre recognition, and that is done by simply computing the Fourier transformation and then computing moments of the spectrum or the magnitude of the spectrum. Moments can be statistical moments such as mean, standard deviation, higher order moments, or might be set of abstract moments. Several do exist. What is important is we want to grab the relationship of a fundamental frequency and the higher level components. And there are different schemes how to do that for different instruments as well. Okay, the most important thing between Fourier transformation and Cosine transformation is at the same time the most important audio feature, and it goes by the name of MEL frequency Spectral coefficients, or simply MFCC. Spectral is an artificial word that was invented for the method. It is a very simple recipe. The first thing is you go to the spectrum by short-time Fourier transformation. Secondly, you apply MEL transformation for getting from the frequency to the perceived pitch. We also had that when we spoke about psychophysics. And in the simplest form, then you employ a DCT, a cosine transformation. So it includes both. There are various variants of the MFCCs. Some in between do a logarithm. Others do an inverse Fourier transformation. Others go Barkhausen band and do a decomposition into different bands and so on. So there are different ways to play this. However, the fundamental recipe stays the same. What are the benefits of the individual steps? And I do this in detail because MFCC is the foundation of music recognition, speech recognition, environmental sound recognition. So essentially everything that matters in audio, here or there, uses MFCCs. In the last step, by the way, after DCT, you throw away almost all coefficients. Typically, you keep the first 7 or 13 coefficients. All the other thousands you throw away. So what are the individual components? Obviously, short-time Fourier transformation brings us with windowing, for example, a Hamming window, into the spectral domain. So all the coefficients now are the similarity of certain almost sine waves to the input signal. Mel transforms these frequencies into perceived pitch. The DCT acts here completely and exclusively as a factor analysis that shifts from the entire spectrum into the first coefficients. And since we did that and got all the information resting in a few coefficients, we can then throw away the rest of the coefficients and just keep the first 7 or 13. And that gives us a very compact description of the signal, a very fast description of the signal, and also a very powerful one. And that is why this operator is of such tremendous importance in the area of audio retrieval. I've even seen it applied on visual signals, for example, bioluminescence computation and then employing MFCCs on that. That, of course, is a hoax. There is nothing like the Mel scale in the visual domain, but the overwhelming impression you get from the good performance is that it might be still interesting. Okay, you won't do that. You will apply it on audio data, could, for example, easily be used to recognize the voice of Kermit the Frog. Yeah, so much for the audio features. In the cosine transformation still has applications in other areas. But first, let's do another one for the Fourier transformation, or a last one for the Fourier transformation, and that is actually visual. It's motion recognition and by optical flow. I will just give you the idea, because Lucas-Canade optical flow is the superior method and state of the art, but there would be an alternative in exploiting what the Fourier transformation has as shift properties. That means that if you shift the input signal, like for example in the case of an image, to the left and to the bottom for a few pixels, and do the Fourier transformation on the original one and on the shifted one, then the spectra will actually be more or less invariant. And this gives you a simple way of computing whether the entire camera was shifted from the left to the right, for example, or whatsoever, by computing the spectrum, comparing the spectrum of the original image and of the shifted one. You know exactly then what the shift would look like in the spectrum, and from that you could conclude on the original transformation, giving you a global idea of the optical flow. If you do that, it is referred to as phase correlation. Because two frames are compared by similarity, not in the time domain, but in the spectral domain, so they are compared not by their samples, but by their phase. Okay, that's the last one. Practically hardly used today, even though it is actually quite fast, because it's just a global description and we are always interested in local events in image. And Lucas-Canade optical flow is qualitatively very, very good. Okay, so what do we have? Cosine transformation is used, for example, in MPEG-7 for color histogram encoding. However, not as a feature, but as factor analysis. To make the resulting description more efficient and putting the information in a few places. In its own right, it is used for texture computation. So employing DCT without a window function, you don't need that there, and picking n coefficients from the beginning gives you a nice description of regularity patterns, of coarseness patterns, and so on, the bigger the first few coefficients, the coarser your description is, and so on. This is also used in MPEG 7, but also in many other places. So you see, it's quite a way to understand integral transforms, but once you got it, the application is manifold and relatively straightforward. In the audio domain, we can do a lot by knowing the individual frequency components, though they are not perfect. No? We can get the melody through the spectral peaks. We can get a basic understanding of the entire content through the MFCCs. We can identify instruments through the timbre features. And we can identify rhythm through the psychophysical linear prediction. On comparison, Cosine transformation in its own right is mostly used in texture recognition and otherwise in different areas, even in the audio domain, as a cheaper variant of principal component or factor analysis. If you've never heard factor analysis, by the way, the lecture block that should be the next in the sequence on semantics in descriptions will explain you what that is. It is a statistical method that you should have heard of in school. Okay, we are almost done. There is only one more domain that we have to cover today, and that is local features. Since it's local, where does it belong? Correct, it belongs exclusively to the visual domain. There is no semantics and local information in the audio domain, nor in most, in biosignals and even in technical data and chart analysis, there can be local information, but not in the audio domain. So what is the whole idea of local features? In the beginning said we have to overcome the gravity of the sample. So these methods are kind of holistic or global. And that relates them to the integral transforms, and that's why we discussed that here. There are two principal approaches. The one is to look for specific points, interest points, in the mass of all points. And the second one is to do an entire transformation. Of locations. Let's look at an example. The typical local transformation, so interest point transformation, endeavors to identify those corners that contain this vast semantic information. This is nothing that was created by a machine. This example, another one from the book, is something that I faked in order to show what would be desired. The image contains basically all the major points of biometric phases, biometric phase analysis. On the left, applied on the original object, on the original image, and on the right, the same is applied on an edge image used with the so-called Kenny edge operator. Okay, so these are just the same points on two different types of images. Would we have a transformation that can do that? We would be very happy. In practice, something like that, unfortunately, does not yet exist, and since the introduction of deep learning methods, these local methods are hardly used anymore anyway. They are used today. If they are used in edge computing. Like in Internet of Things, where you have only limited power consumption requirements or limited hardware requirements, where you cannot use a sophisticated deep net, even though these architectures can also be loaded today on very small processors. But in some limited scenarios, it's simply not possible to do that. And then local features are still relevant. They might be interesting for you, in particular when it goes to the recognition of the peaks in similarity modeling too. But we come to that in a different lecture block. So this is what would be desired when it goes to interest points. How can we do that? Or before we say that, let's ask what is desired with the second approach. The second approach takes all non-bordering locations of an image, so everything that I described by a point here, and describes the neighborhood of it in a predefined way. Okay, so before we look at two examples, I give you the names of those. For interest points, we look at a recipe called SIFT, and for the entire transcoding, we look at something that is called linear binary pattern. Or local binary patterns. And SIFT stands for scale invariant feature transformation. Very old, going back to the early 2000s. LBP comes later, briefly before the introduction of deep networks. Okay, so how does SIFT work? SIFT is yet another recipe. Maybe let's start at the end and then go to the front. All the images that are going to come now are again from the book. These now are real interest points, not ones that I have faked, but these were really extracted by the SIFT operator. What it does is it takes a source image and somehow identifies these interest points. Okay, but then it doesn't store as a summary the location of these points. No, it actually stores neighborhoods of these points, sometimes smaller, sometimes larger, like these, only covering local information as is anyway desired. You see, SIFT is not very efficient. The whole image of the anchor person, which is semantically so highly loaded, the person has a name, he has an expression on his face, there's a lot of other things that are encoded, only comes out with 3 local points. So practice and desire in the area of interest point detection are very far from each other. That's why normally today you would use a convolutional neural network to do that. Anyway, each of these local descriptions, as can be seen in this image, is a gradient histogram. So for the neighboring points, the direction of the steepest ascent of the luminance plus the magnitude are encoded somehow in the image. So that is the procedure. Source, find some interesting points, describe them by a neighborhood, all together and each individually with a complex histogram. Well, how is this done? On this slide we have 2 different procedures. Forget about the left one, I won't mention this one. On the right hand side we have the SIFT. What does it do actually? First of all, it has to identify points that are interesting. For that it employs a method that uses the original image, computes an image with the same size but double coarseness. That can be done by, for example, compressing the image to half its size and then blowing it up again to the original size. That way you lose information. Repeat the process over and over again, and then you end up with such a vertical thing, which is called a scale space. If you don't do the blowing up step again, you end up with the so-called image pyramid. Okay. SIFT employs this scale space thing. So taking the original image, compressing it to half the size, blowing it up again, and so on. And computes interesting points in a very primitive way by saying that compare 2 of these levels of the scale space. And if there is a point that is invariant, that is here on the one and on the second level as well, then this is a candidate of an interest point. They call it difference of Gaussians, because this reducing and increasing the size is similar to a Gaussian blur operation. Once the interest points have been detected, some are thrown away, in particular those that are too short or only appear on 2 neighboring layers and not on 3 maybe. Then you look for the secondary weight of the image information, and if that one is not significant enough, we don't go in detail through this part, then you throw it actually away as well. For that we employ the Hessometrics, which is the secondary weight of a matrix. The eigenvectors of that describe how significant the points are. The longer the eigenvectors, the more significant. If that relationship is beyond a certain value, then we throw away the point because it's probably not an isolated corner point. And with interest points, we are interested in isolated corner points. Anyway, in the last step comes this building of the histogram. We compute the gradients, set a threshold for what is interesting, only the very long gradients come into the computation, and then we build the histogram. That is a typical local feature method. It's still there, for example, in OpenCV, and if you are in the situation where you cannot use convolutional networks that build something similar but implicitly from training data, for example in edge computation, you can try to go for that feature. It gives you, in the end, it gives you a vector of the data to use that for the computation of an image description. Okay. Alternatively, the idea of the local binary patterns is to take 3 by 3 neighborhoods, put out the center, and then for the 8 neighbors compute whether the neighbors are smaller or larger than the center. So the center, though randomly picked, gets a higher semantic load. If these values, if these values are smaller, then we give them a 0, like 3, 4, 2 are smaller, all the others are bigger. And we end up with something like this. And this is then, like in a hashing function, encoding into a vector of bits, saying that starting from the top left and going in circles, and here, of course, from the right to the left, 1, 0, 0, 1, 1, 1, 3, 6, 7, 8. So, and that can be then stored as an integer value or an unsigned integer value and gives you information on the locality. Well, that is quite crude, of course. You wouldn't use the linear binary patterns as a feature by themselves, but based on that, for example, compute edge information or do a DCT or do something else. So it's kind of a pre-processing method. It is still awkward. Why do we use that? Because individual samples in the image information usually don't matter very much. We want to get away from the importance of this information. There is, however, only little way except integral transforms to do that, to achieve that. And the LBPs have been an attempt, actually quite successful one, to, without the need for semantics, there are hardly any, to encode at least these 3 by 3 neighborhoods in a standardized form, and not the individual values anymore, but the patterns, these small patterns. So the typical application is, once you have computed the patterns for every location, to build a histogram for the different types with the numbers of occurrences, and thus describe the image information, hoping that these 3 by 3 patterns hold some information. If not on the local level, then you can combine that stuff with a scale space and compute the histogram for every scale, from very fine to more coarse, thus providing you image information. Apparently, these local features are not able to load something with high levels of semantics. That job would have to be done by the classifier that employs these data. They did, however, in the old days get you away from the individual sample at least to the level of groups of samples, of neighborhoods. So similar to what an edge operator did, but without that hard thresholding that you have in edge computation. There you have one threshold, and if you're below that, like in a Laplacian operator, then the whole neighborhood goes to zero, which is not desired in all cases. Okay, there is no doubt that these methods today, SIFT and both LBP, are dominated by deep networks. The only justification for still keeping them in the game is that in certain scenarios, in particular on the edge, as we say, when computation power is limited, these methods can build an alternative. And of course, they are conveniently implemented in the big libraries, including the OpenCV library, which you are free to use in your lab course. And therefore, it wouldn't be wrong to try it on detecting, for example, maybe Waldorf and Staedtler. I doubt that you can detect Kermit the Frog because his green is quite unique. There, I would rather transform to the luminance channel and see if cosine transformation gives you a set of coefficients that is typical for Kermit. Probably with linear binary patterns, you will not be able to grasp Kermit. But maybe I'm wrong. It might be that the fur, the texture of the fur, actually has a distinct peak in such a histogram. But more on that in the last part of the lecture when we speak about what you can do in the lab course. That was it for today. The rest that will come is a lecture block on how you actually introduce semantics, because here they are very low, in other features they are higher. In the end, you want to reason similar to how human beings do, as we saw in the lecture on perception. And in the very last block, we will then talk about the sophisticated machine learners, including long short-term memory, support vector machine, and Gaussian mixtures. Last thing to do, let's have a look at the educational goals. I think you understood the role of integral transform. If you keep in mind that they were done for a different purpose, going to the spectrum, using the desirable properties, going back again. We don't have to go back again. Therefore, Fourier transformation gives us a uniform distribution of the spectrum. Cosine transformation discriminates to the first coefficient. Fourier transformation and cosine are both good and usable for us because they describe sine waves. And those we can easily interpret as long as they are combined by convolution, by similarity with the sample data. Okay, that's it in a nutshell. We have a toolbox of spectral features, most importantly MFCCs, spectral peaks, and psychological linear prediction. Phase correlation is hardly used today, I have to admit, because Lucas Canada is so much more convenient. And the DCT is just used as a factor analysis and not really as a feature. Still, many transformations do employ it to the benefit of the results and of the speed of the process. Eventually, we have a small toolbox of local features. In particular, we saw what SIFT is. It's an interest point detector, not very intelligent, but very fast, and in the holistic sense, expressive description on a rather low semantic level. It's omitted. And we have the linear binary patterns, another attempt in an integral way to get away from the gravity of the sample and get a bit more of stability of meaning into the data. Thank you very much for watching. As always, if you have questions, please put them in the forum, get in touch with your lecturer. The link to the forum is given at the end of the lecture, but as well in the TU information systems. I hope you enjoyed this lecture, and that it helps you in your lab test in media in Similarity Modeling 1 and 2.